I want to talk to you about eval and exec. I want to talk about how these work, whether they should ever really be used in your work, where they may come up, and a little bit about what they tell us about Python beyond just two tools that allow us to run code. And so let's take a look. We know that there is a function in the built-ins called eval, and we can call it with a string that contains some Python code, and it evaluates that Python code. Eval is short for evaluate. Here you can see it prints the value 2. There's also a function exec that appears to execute some code, but it may not be clear to us what the difference between evaluation and execution is. If in our exec we put something like a print, we can see the output is visually printed to the screen, but this exec function appears to return no value. Well, I want to share with you one important consideration when you're thinking about Python, whether you're a beginner or an expert. Python has what you might call a statement expression dichotomy in its grammar. Python distinguishes between expressions, which are pieces of code that compute values, and statements, which are pieces of code that perform actions. Let me show you an example. Def F in Python means perform the action of creating a function. F open close parentheses means give me the expression, compute a value by calling this function. These two pieces of arithmetic operations, plus and multiply, they compute a value. They compute whatever the addition of these two values are, whatever the multiplication of these values. These 3 lines here are executable Python code that mean go off and perform an action, go off and create a class. This line of code says use that class definition to create an instance and assign it to a variable name, and then perform some attribute access. When you look at this, it may be difficult for you to really get a sense of what the distinction between the expression and the statement grammar is. Here's the general perspective that you should take. Basically, in Python, everything is executable code. Almost everything is executable code. And so every line of code is being run. It has some bytecode behind it. And if that line of code returns a value, then it's probably an expression. If that line of code performs some action where the consequence of that might be visible in the local scope, in the global scope, maybe visible as a consequence of some other stateful thing that happens, then it is likely a statement. If we think about something like the import statement, this is a statement. The class statement for creating a class, this is executable code and a statement. The def statement for defining a function or a generator, this is a statement. If, else, elif, these are all statements. Well, it turns out in Python, we actually have some duality around these. For example, there's oftentimes a statement and an expression way to convey the same general idea. Here we have a for loop. This is clearly a statement. Go and do the looping. And the expression version of it might be something like comprehension syntax. Here, go and perform the looping, but give me a result value. In this case, whatever the consequence of this looping provides. If this is a, for example, comprehension syntax with a list comprehension, then that list. Here, it may be down to whatever we want to do with this generator expression, how we want to consume it. While true, it's a statement. Go off and loop forever or until I break. A comprehension syntax, a generator expression, or a list or set or dictionary comprehension, looping over an infinite sequence, well, that's the equivalent of while true in the expression grammar. If else, these are statements. They don't return values, but there is an expression form of it, the ternary if else, that returns a value that you can then bind to the name x. Def f, it's a statement. It has a consequence in the world, that is, it creates in the local scope a function named f, but it doesn't return a value, whereas lambda actually returns a value. This is another dichotomy between a statement way to express create a function and the expression way to create a function. Even classes have the same thing. This is the statement way to express a class. Its consequence is visible in the local scope, but it doesn't return a value. We can't say x equals class t, but we can say t equals type using the 3-argument type function. This is the expression version of defining a class. Even importing a module, this is the statement version of importing a module, and this is the expression version of importing a module using the built-in _import function or using import lib, import module. And this, we can actually look at the consequence of the value. We can print it to the screen. We can assign it to a variable. In this case, we probably actually want to assign it to a variable to make use of it. Even things like assignment. Assignment historically in Python has been a statement. Go perform the action of creating this name binding, this relationship between a name and a corresponding value in the local scope. Well, now in Python 3.7 and later, we have an expression version, the assignment expression syntax, that you can actually look at the consequent value of, or you can do something with this consequent value of. The difference between exec and eval is Eval is for evaluating singular Python expressions. Eval takes a string with a single Python expression, that's it, and it evaluates it. And it gives you what the result is. Exec takes a string with one or more lines of Python code, which could be statements and expressions, and some namespaces, in this case just a dictionary, which represent the local and the global scope. And if you want to see the consequence of it, you may need to reach into that namespace and pull the names that were bound out here. Now, I want you to consider one other thing before we talk about eval and exec. Let's think about metaprogramming approaches that we have that lead us in the direction of eval and exec. We have metaprogramming approaches in Python like the decorator. And the general pattern is anytime we're writing a lot of functions, and every time we define a function, we do something. We update the documentation of this function, we add some lines before and after this function, we register it in some system, whatever the case may be. Every time we see that we're defining a bunch of functions and there's some common action that we do every time we define that function, that's basically metaprogramming with decorators. And so here, the example of these 3 lines of code, or this line of code here that might be repeated, we might solve writing a simple decorator that puts those lines of code in one place in a dynamically defined function, and then we apply that behavior. We modify this function by replacing it with a brand new function that includes that line of code using the decorator syntax. It may be the case that we might wonder, well, is there a case where we need to use metaprogramming to create a function dynamically? In decorators, we do that, but how about just create the function from scratch? Not take an existing function and do something alongside it, but create it from scratch. And we can actually do that in Python. We can do that with just basic functional programming approaches. We can define functions as executable code and return them. And so here you can see we have some function called create function, which goes off and creates a brand new function. So we create f, g, and h without using that def syntax, dynamically creating these. And you can see there's some modality that's passed in that's deciding how we choose which function to return. You might wonder why we want to do this. Well, the reason we want to do this is instead of having one function where that modality is evaluated at runtime, and this valuation may be expensive, it may be clumsy, what we can do is we can say, you know what, I'll statically, at the creation of this function time, I'll statically create different functions which look very different, which presume that that modality had already been evaluated, that already have all of the assumptions. Like, for example, one of these might be, this mode might be what platform you're in. So this is the version of the function that runs on Linux, and this is the version of the function that runs on some BSD equivalent. Whereas here, do we really want to be checking what operating system you're in at runtime in the body of this function? It's not going to change over the runtime of this program. It's not like the program's going to start on Linux and end on Windows. That's not really possible. And so, do we really need to make that a runtime check? No. And this is why we might dynamically create functions in that fashion, as opposed to just checking the modality at runtime. Well, we actually do this fairly often. You can think that if it's the case that we want to prevent somebody from having to worry about a modality, and we want to presume a modality that's kind of fixed, we might use something like functools.partial, so that modality would still be evaluated at runtime, but we fix it in place so that somebody who uses F, G, or H doesn't have to know that this is F with this mode, G with this mode, or H with this mode. But between you and me, I don't really like functools.partial, in part because I feel like it's less flexible than just writing a Lambda, just dynamically creating a function using this expression syntax for creating a function. And I don't really see, other than the wraps mechanism, what functools.partial really adds on top of just doing something similar like this, which doesn't actually require one import. So I guess we're tied with the number of imports that we have. When we use decorators, there's not just function decorators, but there's also class decorators. And if we think about the decorator pattern for functions, it's every time we define a function, we do something. Well, for classes, it's the same idea. Every time we define a class, we do something. We add attributes to this class. We check that this class has things that it's supposed to have. We wrap certain functions in this class. We register, we add documentation. And it's the same general pattern. So far, none of this seems to require eval or exec. Well, let's dig a little bit deeper. In addition to class decorators, we also have init subclass and metaclasses. And the init subclass metaprogramming is every time we subclass from something, we want to do something with that subclass. Ensure that that subclass has implemented important methods. Ensure that subclass is valid in some fashion or another. Add extra methods. Register it in some fashion. We want to do something every time we inherit from some base class. And that's the general idea with the meta class as well. Do we ever dynamically create a class like this? That's actually fairly rare, but you could think that it could be something that we might want to do because everything in Python is executable code. And so we can put a for loop in a class body that runs some executable code, loops over some input data, checks some modalities, makes some choices, and decides what it wants to create in the class body. Here, this create class will create a class with whatever methods you ask it to create it with. A, B, C, D, and E will all exist. And it does it by dynamically defining this class with a for loop in the class body and assigning to the scope that the class body uses to create the class attributes. Well, would you really write the code this way? I think that there may be some circumstances where if you had some really some transformations and you could break them down into steps, you wanted to make them very clear, you might write the code this way. But that 3-argument type function that can also create classes where it takes the name of the class, the base types of the class, and a dictionary containing the body of the class, that might be preferable because you could just kind of set up what the body of the class looks like and then use this 3-argument type function. Is there a strong benefit to one of these or the other? Not really. Where does exec and eval come in? Well, let's think about it. What if we needed to define a bunch of different classes? And we were finding that it was really painful to do that. Like we have some sort of distributed algorithm and we need to represent the messages that are passed back and forth. And there's many different types of message. We don't want to just have one class method, which a bunch of attributes, which may or may not be filled in. We really want to have a propose message, an accept message, a reject message, a commit message with their own distinct attributes, where we can do things like is instance on them. And it says, yes, I'm a propose message, not look at message.type and then dispatch based off of that, where we can maybe make assumptions that there are certain behaviors that are unique to these that just exist if we're in that type, that type of message, where we might even want to use something like the match and case statement in Python in order to say, oh, if it's of this type, do this behavior. If it's of that type, do that behavior, and just have everything work. And so you could think that we might have lots of these classes that we create for each individual type of message. And it's a lot of boilerplate for us to write a bunch of these class statements, even if they're data classes, to establish their attributes, to say which methods they do or don't share and whatnot. And so this may be the case where we want to use this we want to use this type, 3-argument type, and we might want to dynamically decide, what the init looks like. But if we do it this way, our init kind of generic, it takes star args and star quargs. If we do a help on this propose, you can see there's all sorts of small details that aren't quite as nice as we want them to be. Like we can't quite see what the init is. We can set up the doc pretty easily because it's just an attribute that we set. But there's a couple of these details where we can't quite get them just right to make this look as though we had just did class. So when we want to use metaprogramming to simulate the human action of write some code, but to make use of the computer to do that in a automated fashion, that's where we might use eval and exec. Instead of using the previous approach, what we might do is we might set up the template and kind of pretend that we had just written class propose, class accept, class reject. But instead of going through those mechanics ourselves, we might have this create class function actually fill in this template with the field that it wants, do any sort of adjudication of certain modalities that it needs to do any checking of this, give you any flexibility that you want in order to define things or in order to toggle between different choices, and then just exec it in some namespace and return that exec value. When you look at this, you might say, oh, that's kind of ugly. It's not as systematic. It's not as constrained as the 3-argument type or the other approaches. But I think you have to make a decision when you're using like exec and eval. You really have to decide, is the ad hoc flexibility of exec and eval worth it over whatever contortions or whatever extreme mechanics I have to come up with in order to get this to work with type or the 3-argument type or the other mechanisms? And these kind of metaprogramming approaches are very ad hoc. They change very quickly. There may not be a defined structure. That structure may change over time. Maybe the exec or eval preserves that flexibility because it's really just string manipulation, and it really just exposes the details that you care about. For example, the 3-argument type exposes details like what the subclasses are, what the bases are. Are you really going to be, parameterizing over the base types? Probably not. You're more likely to be parameterizing over the methods. And so here you can think, in some ways you can automatically create methods just via string manipulation mechanisms. If you think about this, one other interesting thing is when you have these deep metaprogramming approaches, it can sometimes be really tricky for somebody to figure out where did this proposed class come from? Well, they're going to have to search for this and figure out what module it was imported from, and maybe they're going to grep through the source code. But think this pattern is actually pretty hard to grep for. Something equals. The class message pattern is really, that's what you grep for. It's really easy to grep for, and you would expect it would be class and some number of spaces and then the name of the class and then maybe open close parentheses optionally. Whereas a name binding, you can imagine there could be all sorts of false positives if you were to grep for the name binding. Well, if you use exec and eval, you don't really get an advantage here, but you can see exactly what the output looks like. You can debug this pretty nicely. You can just print out what the source looks like and say, okay, that's exactly what this is going to create. So if you were able to find the source of what creates these different classes, you can debug it very easily and see exactly what you're getting. That's one advantage of the exec or the eval. And another advantage is, who says you actually have to use exec and eval directly? Why not have the thing that creates your subclasses just return a string? And it'll return a string with the code that it creates. And when you actually want to run this, you write this to a file in a temporary directory, and then you just import from that file. Here's the deal with exec and eval. You cannot avoid them in Python. Fundamentally, in Python, your Python interpreter, unless you're working with the very, very rare code-signed Python interpreters. This is one project that I worked on for a cloud provider years ago, and I think there's only one instance of these things in the world. But unless you're working with that, your general Python interpreter can run any code that's written in source text in a .py file in a specified directory. Python interpreter does not lock down where those directories are. Your user code can add directories to the sys.path as it desires. Your user code, if it can write to files, can write Python code to a file, add that file to the sys.path, and import from that file. Import, because it works off of source text, must necessarily internally make use of exec and eval. Internally, in fact, it uses exec, or an equivalent of exec. Therefore, what you can think is exec and eval are not actually things you can avoid. They exist somewhere in your code base, and they should be used judiciously. And the place where they should be used judiciously is, one, you have some really ad hoc metaprogramming you want to do, but you want to get it as close as possible to the actual process of a human being writing out the functions or the classes that they wrote out. Two, you might want to have the ability to cache that metaprogramming into like a generated file to make it really easy to grep, because you can think, if I were to commit this generated file to my repository, then somebody could easily just grep for class propose. And you could just give them some indication that if the generated file is out of date, or you could have some sort of caching mechanism that identifies where it needs to rerun this file, or whatever the case may be. But you can give somebody a lot of visibility on what's happening here that some of the other metaprogramming approaches don't give you. Our conclusion, thus, is eval and exec are useful metaprogramming tools. They're not really avoidable in Python, and they really should be used in cases where you want to get as close as possible to what a human being is doing, just writing out that source text. Because you can see in the previous example, I basically mimicked the process of writing out some source text and writing it to a file. Well, that's where you might use exec and eval.